Hello there, and welcome to the Sleepy Science Channel. Tonight, as you settle in, let your thoughts drift into the stillness of the evening. Imagine the quiet sky above you, a vast doe scattered with countless stars. Each point of light is a distant sun, burning steadily across gulfs of time and space. In those distant suns, there may be worlds circling, perhaps as rich with oceans and clouds as our own Earth. And yet, despite the immensity of it all, the night remains silent. No messages reach us. No other voices call across the darkness. It is a silence that carries with it one of the deepest mysteries in science. Tonight, we'll explore the Fermi Paradox, the puzzling question of why a universe that seems so fertile for life appears to be so empty. Together, we'll drift through possibilities, examining the origins of the question, the many answers that have been proposed, and what the silence might mean for us. If you enjoy these gentle journeys, I invite you to like and subscribe, or simply share your thoughts down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, allow yourself to settle. Let your body grow still, your breathing soften, and your thoughts slow down like ripples fading on a quiet pond. The night is wide and calm, and there is no need to hurry. Simply rest here, safe beneath the stars, as the story unfolds. Now, let's begin. When we lift our eyes toward the night sky, we see only a fraction of what lies beyond. The stars that punctuate the darkness are nearby neighbors, glowing across short stretches of interstellar space. Yet beyond them, the universe stretches outward without end in every direction we can observe. The portion that astronomers call the observable universe is limited only by the distance light has traveled since the beginning of cosmic time. That boundary lies some 46 billion light-years away, defining a sphere of almost unimaginable scale. Within that volume, the number of galaxies alone is counted not in thousands or millions, but in the trillions. Each of those galaxies is home to vast assemblies of stars, clouds of dust and gas, and structures of bewildering complexity. Against such immensity, the small blue world we call Earth seems fragile and temporary, a brief flicker of chemistry and biology in a cosmic ocean, but should, by every reckoning, hold countless other lights of life. Within our own Milky Way galaxy, the scale remains staggering. Current estimates suggest between 100 and 200 billion stars scattered across a disk more than 100,000 light-years wide. Many of these stars are orbited by planetary systems, and surveys of the sky using sensitive instruments have revealed that planets are not rare anomalies, but common companions. Some are massive gas giants circling close to their stars. Others are rocky worlds, cousins of our Earth, orbiting in quiet arcs that last months or years. The discovery of exoplanets, confirmed in the last few decades, has shown us that planetary systems form as a natural part of star birth. Dust and gas collapse into shining suns, and the debris coalesces into worlds. To look at the Milky Way is to see not just stars, but a vast assembly of possible homes, perhaps billions of places where life could, in principle, take root. Yet stars and planets alone do not guarantee the spark of life. Conditions matter. The presence of liquid water, the right range of temperatures, the stability of climate over long periods of time, and the presence of key elements like carbon, nitrogen, and oxygen all shape the potential for habitability. Astronomers often speak of the habitable zone, the narrow ring around a star where temperatures could allow oceans to remain unfrozen and unfried. But habitability is not limited to distance from a star. Moons heated by tidal forces, subsurface oceans sealed beneath ice, and atmospheres rich in chemistry may all harbor niches for biology. The more we study, the more we find that potential habitats are not rare but widespread. The very ingredients for life appear scattered generously across the galaxy. When scientists reason about these numbers, the conclusion seems obvious. If there are hundreds of billions of stars in our galaxy alone, and a significant fraction of those stars host planets, then the number of potentially habitable worlds must be measured in the billions. If life is not an extraordinary fluke but a process driven by chemistry, then it seems likely that it has arisen many times. And if evolution tends toward complexity given enough time, then intelligent civilization should not be unique to Earth. Probability suggests that somewhere in the long corridors of cosmic time, others must have looked up at their own skies, asked their own questions, and wondered whether they were alone. The silence we experience should be temporary, a gap before discovery. And yet, despite our careful listening, the stars remain mute. It was in the middle of the 20th century that the paradox came into focus, with a remark made almost in passing. In the 1950s, during a casual lunch with colleagues, the physicist Enrico Fermi is said to have posed a question that has echoed ever since. As the conversation drifted to the possibility of extraterrestrial civilizations, Fermi asked simply, "Where is everybody?" The phrasing was plain, but the implications profound. Given the scale of the galaxy, the abundance of stars and planets, and the billions of years available for civilizations to arise, our skies should be filled with signs of others. Ships crossing the interstellar void, signals flashing across space, structures reshaping starlight. Something should be visible. Instead, we see nothing. The question that began as a lunchtime remark has become a central mystery of modern science. The reactions to Fermi's question revealed both fascination and unease. On the one hand, the silence of the stars could be explained by practical limits. Perhaps interstellar travel is harder than we imagine. Perhaps communication is fleeting or fragile. On the other hand, the absence of evidence carried with it a more unsettling implication. If civilizations do not last, if they burn out or collapse before reaching beyond their home worlds, then the silence may be a warning. In the decades since, as we have built radio telescopes, launched probes, and scanned the heavens for signs, the silence has only grown louder. Each improvement in technology expands our reach, yet no whisper has come. The paradox is not just a curiosity, but a tension, a gap between expectation and observation. We live in a galaxy that should be alive with voices, but we hear only our own. Enrico Fermi was no stranger to big questions. By the 1950s, he had already established himself as one of the great figures of 20th century physics. His work stretched from quantum mechanics to nuclear physics, from theoretical insight to hands-on experimentation. He had built the first controlled nuclear reactor, contributed to the development of particle theory, and mentored generations of students. By the time he sat down at that famous lunch in Los Alamos, his reputation was secure. The world itself was in transition. The 1950s were marked by both optimism and anxiety. Rapid advances in technology, the dawn of the space age, but also the shadow of nuclear weapons and the Cold War. The idea of civilizations beyond Earth was not yet a scientific discipline, but it was part of the atmosphere of speculation. In such a climate, Fermi's simple remark had weight. It was not a whimsical thought, but the distillation of physics, astronomy, and probability into a single, unsettling question. Although Fermi's phrasing was new, the thought that other worlds might harbor life was not. Centuries earlier, philosophers and naturalists had speculated about plurality of worlds. Giordano Bruno in the 16th century imagined an infinite universe filled with suns and planets, many of them inhabited. By the 19th century, astronomers peering at Mars with telescopes debated whether they were seeing artificial canals, signs of a dying civilization clinging to survival. While these ideas often blurred the line between science and imagination, they reflected a persistent curiosity. If Earth is not the center of the cosmos, then why should life be confined to it? The shift from myth to science had already made the universe larger, older, and stranger. The question of life elsewhere was waiting, poised between poetry and calculation. By the middle of the 20th century, technology gave the question new tools. Radio astronomy was emerging as a powerful way to study the heavens. Instead of relying only on visible light, scientists could now listen to the sky across a wide spectrum. This opened a path not only for understanding stars and galaxies, but for searching for artificial signals. The idea that an intelligent civilization might broadcast or leak radio emissions was compelling. In 1960, Frank Drake conducted Project Ozma, the first deliberate attempt to tune a radio telescope to the stars in search of an extraterrestrial transmission. He chose nearby sun-like stars, listening for weeks. No signal came, but the experiment marked a beginning. What had once been speculation became a program of systematic observation, later formalized as the Search for Extraterrestrial Intelligence, or SETI. To make sense of the scale of the problem, Frank Drake proposed an equation, not as a formula to be solved, but as a way to break the unknown into parts. The Drake equation multiplied together factors: the rate of star formation, the fraction of stars with planets, the number of habitable worlds per system, the likelihood of life, the likelihood of intelligence, the lifespan of civilizations, and so on. Each term represented a step, from physics to chemistry to biology to sociology. The power of the equation was not in precision, but in framing. It showed that the question was not mystical, but quantifiable. By adjusting the values, one could move from a galaxy teeming with civilizations to a lonely universe with only one. The ranges that emerged from the Drake equation were vast. For some values, the product suggested thousands or millions of civilizations in the Milky Way at this very moment. For others, it dwindled to nearly zero. The uncertainties were immense, but the very structure of the equation made one thing clear. Unless several of the steps were extraordinarily unlikely, we should not be alone. If even a modest fraction of planets produced life, and even a modest fraction of those produced intelligence, then the galaxy should be busy. Civilizations could rise and fall, but over billions of years, enough should exist simultaneously to be detectable. The silence, therefore, was not trivial. It suggested that somewhere in the chain of terms, there must be a bottleneck, a filter that narrows the outcome. Whether that filter lies in the origin of life, the rise of intelligence, or the survival of technology remains unknown. This is why the paradox refuses to fade. With every new discovery of exoplanets, with every refinement of astronomy, the expectation of abundance grows stronger, not weaker. Yet the observations remain unchanged. No confirmed signal, no evidence of visiting craft, no ruins scattered among the stars. The paradox sits at the intersection of probability and reality, like a riddle that deepens each time we approach it. To ignore it is difficult, because it forces us to confront not only what might be out there, but what we are here. In asking, where is everybody? Fermi gave us more than a puzzle. He gave us a mirror in which to see our own place in the universe, suspended between silence and possibility. When we think of time, we often measure it in years or decades, in the rhythm of human lives and generations. But the universe keeps time on scales far larger than we are accustomed to. Stars, the basic engines of galaxies, are born, live, and die, over spans that make human history appear fleeting. Small, dim stars known as red dwarfs may shine steadily for trillions of years, longer than the current age of the universe itself. Even stars like our Sun, moderate in size, burn for billions of years before exhausting their fuel. Galaxies, too, are not temporary structures. The Milky Way has persisted for more than 10 billion years, cycling through generations of stars, collisions with smaller galaxies, and waves of formation and destruction. Against such an immense backdrop, the window for life to arise and flourish is broad. Civilizations are not pressed by cosmic clocks. There is time, seemingly more than enough, for life to appear, to evolve, and, if capable, to spread. When these cosmic timescales are compared to the timescales of civilization, the contrast is striking. Human civilization, in any recognizable form, has existed for only a few thousand years. Our use of radio, electricity, and advanced technology spans just over a single century. And yet, even in that brief moment, we have altered our planet, built machines that orbit beyond the atmosphere, and sent probes into interstellar space. If we imagine a civilization surviving not just centuries but millennia, or even millions of years, the possibilities expand dramatically. The lifespan of stars provides immense windows of opportunity. A technological society might arise early in a star's life and still have billions of years of stability ahead. Measured against the vast age of the galaxy, the growth of civilization is like a spark with the potential to become a flame that spreads quickly across the dark. Even if we imagine that interstellar travel is slow, the numbers remain compelling. A spacecraft traveling at just 1% of the speed of light could cross the galaxy in about 10 million years. This sounds long to us, but set against a galactic history measured in billions of years, it is quick. Colonization does not need to be fast to be effective. If a civilization launched probes or colonies that advanced incrementally, spreading system by system, they would eventually reach every corner of the Milky Way. 10 million years is a fraction of a galactic lifetime. Even slower expansion, measured in tens or hundreds of millions of years, would still allow complete settlement long before the present era. The scales of distance and time align in such a way that expansion, once begun, seems inevitable. This is why even modest assumptions about travel lead to startling conclusions. A civilization that spread at leisurely speeds, pausing for centuries or millennia between steps, would still fill the galaxy within a sliver of cosmic time. Each colony could, in turn, become a hub for further expansion, creating a chain reaction that extends across the stars. The process need not be continuous or efficient. It could be patchy, uneven, and slow. Yet given enough time, even such halting progress would reach everywhere. The mathematics is difficult to escape. When billions of years are available, even the most conservative rates of expansion are sufficient. The Milky Way is not infinite. It is a bounded structure with a finite number of stars. Against the patience of the cosmos, the distance between them shrinks. If this is true, then one implication follows with force. If technological civilizations have arisen at any point in the distant past, they have had time to expand widely. Our own sun is a latecomer, only 4.5 billion years into its life. The galaxy was already ancient when Earth formed. Stars older than the sun may have hosted planets, and those planets may have seen life evolve long before our own world cooled. Civilizations could have risen hundreds of millions or billions of years before us. If they endured, their traces should be visible by now. Even if they did not survive indefinitely, the remnants of their presence, signals, artifacts, or modifications of their environments might remain. The deep history of the galaxy makes it difficult to argue that we are simply too early. We are, by all reasonable measures, late arrivals to a stage that has been set for eons. This leads to the most pressing form of the paradox. If civilizations expand, endure, or leave marks, then the galaxy should be filled with evidence. We should see technological signatures in the sky, altered starlight from vast structures, radio signals drifting across space, patterns that betray engineering rather than nature. Even if civilizations are rare, the passage of time multiplies their opportunities to spread. The silence we encounter is therefore more than puzzling. It contradicts what we would expect. The scales of time and distance, when taken together, strongly suggest that others should already have been here. That we see no trace at all forces us to question assumptions at the root. Are civilizations rarer than probability suggests? Do they fail to last? Or is there some deeper reason that the galaxy appears empty despite the patient march of time, but should have made it full? To consider why the galaxy might be silent, we can start with the very beginning of life on our own planet. Earth formed some 4.5 billion years ago, a molten world gradually cooling, bombarded by asteroids and comets. Within a few 100 million years, conditions stabilized enough for oceans to spread across its surface. In those waters, something remarkable occurred. Molecules organized into structures capable of self-replication and metabolism. However it happened, this was the crossing of a threshold from chemistry into biology. The earliest fossils and chemical traces suggest that life was present on Earth more than 3.5 billion years ago. This means that, relative to the planet's age, life appeared quickly. From a cosmic perspective, the step from a lifeless world to a living one did not take long at all. But whether that speed indicates ease or luck is a question we still cannot answer. The process by which life originates, known as abiogenesis, remains one of science's greatest mysteries. Laboratory experiments have shown that under certain conditions, simple organic molecules can form spontaneously from basic ingredients. Amino acids, nucleotides and lipids, the building blocks of proteins, DNA and cell membranes, can arise through natural chemistry. But the leap from molecules to a self-sustaining system is enormous. How did chains of nucleotides first begin to copy themselves? How did early membranes trap useful chemistry without falling apart? And how did these fragile beginnings survive in the harsh environment of early Earth, with ultraviolet radiation and frequent impacts from space? Each of these steps may involve improbabilities stacked atop improbabilities. It is possible that the emergence of life required an intricate sequence of accidents, each unlikely, but together producing something unique. If that is the case, then Earth's history may not be typical, but exceptional. Still, planets and moons across the galaxy present environments that could support such chemistry. Life, as we know it, is built on carbon, hydrogen, oxygen, and nitrogen, elements forged in stars and scattered widely. Water, so central to biology on Earth, is abundant in space, found in ice, vapor, and liquid reservoirs. Planets with rocky surfaces, active volcanism, and atmospheres may provide the right laboratory for prebiotic chemistry. Even moons far from the warmth of a star can be heated internally, maintaining liquid oceans beneath ice crusts. Jupiter's moon, Europa, and Saturn's moon, Enceladus, are prime examples within our own system. If chemistry is sufficient, then planetary diversity ensures that many experiments are running simultaneously across the galaxy. The challenge is not whether environments exist, but whether the spark ignites within them. One piece of evidence that argues in favor of life's resilience is the existence of extremophiles. On Earth, organisms have been found thriving in conditions once thought impossible. Microbes live near hydrothermal vents at the bottom of oceans, surviving in water heated to near boiling and laden with toxic chemicals. Others inhabit acidic pools, salt flats, frozen tundra, and even the upper atmosphere. Some survive intense radiation, while others withstand desiccation for decades before reviving. These examples show that once life begins, it adapts with extraordinary tenacity. This broadens our understanding of what counts as a habitable environment. Instead of requiring Earth-like conditions, life may find niches in places we would consider barren. If extremophiles are any guide, then the galaxy's potential habitats multiply dramatically, from warm ponds to icy crusts. What is rare may not be survival, but the initial spark itself. And yet, a counterpoint emerges from Earth's timeline. The appearance of life was not delayed by billions of years, but occurred relatively quickly after the planet stabilized. This could suggest that the conditions for abiogenesis are not impossibly strict. Perhaps given water, energy sources, and basic chemistry, life arises as a natural outcome. Some scientists argue that the speed with which Earth produced organisms makes life likely elsewhere. If so, the paradox deepens. Because if beginnings are common, then the silence must come later, at the stage of complexity or intelligence. The rapidity of Earth's transition from lifelessness to life leaves open the possibility that the first step is not the bottleneck, but that later hurdles prove more daunting. This leads to a final question within this theme. Is intelligence an inevitable product of evolution, or a rare accident? On Earth, for billions of years, life remained microbial. Photosynthesis, respiration, and simple multicellularity developed. But the leap to complex organisms took extraordinary time. Intelligence, in the sense of tool use, language, and culture, has emerged in only one lineage, our own. Dolphins, crows, and primates show glimmers of it, but only humans have built civilizations. Was that outcome guaranteed, or contingent on countless coincidences? Some evolutionary biologists argue that intelligence is adaptive, providing flexibility and problem-solving that confer survival advantages. Others suggest that it is a freak result, not a predictable endpoint. If intelligence is not inevitable, then most planets may remain rich in life, but poor in civilizations. Oceans may teem with microbes and even multicellular creatures, yet never give rise to societies that gaze at the stars. In that case, the silence is not a paradox, but an expected reflection of rarity. Civilizations like ours may be rare sparks, bright but isolated, in a galaxy otherwise alive but voiceless. When we look at Earth's own story, one of the most striking features is the immense gap between the origin of life and the emergence of complexity. Microbial organisms dominated the planet for more than 3 billion years. Oceans, rivers, and soils were filled with single-celled life, carrying out photosynthesis, metabolizing minerals, and altering the atmosphere, yet never moving beyond simplicity. The step to multicellularity, where cells coordinate, specialize, and form bodies, is not trivial. It requires new genetic controls, mechanisms of communication, and strategies to prevent cheating among cells. This long delay suggests that even if life arises, the transition to more elaborate forms may be an uncommon leap. The rarity of multicellular organisms in Earth's early fossil record underlines the point. Complexity is not an inevitable path, but one that may depend on improbable alignments of biology and environment. When complexity finally did emerge, it was accompanied by a burst of diversity known as the Cambrian explosion, roughly 540 million years ago. In a relatively short span of geologic time, the fossil record shows the appearance of nearly all major animal groups. Creatures developed shells, eyes, legs, and sophisticated body plans. The Cambrian explosion marks a threshold where evolutionary innovation accelerated dramatically. But the fact that it occurred so late in Earth's history raises questions. Was it triggered by rising oxygen levels in the oceans, providing fuel for larger bodies? Was it a consequence of ecological pressures, predator-prey dynamics that drove innovation? Or was it simply a fortunate accident, an evolutionary lottery win that reshaped the biosphere? Whatever the cause, it highlights that even once multicellularity exists, the flowering of diverse and complex life is not guaranteed. The silence of the galaxy might therefore reflect countless worlds where life remains locked in microbial simplicity. Beyond complexity itself lie further hurdles. For a civilization to emerge, evolution must produce intelligence, communication, and cooperation. Intelligence alone is not enough. Octopuses are highly intelligent, capable of problem-solving and even tool use, yet they have not built collective societies. For social intelligence to flourish, creatures must communicate effectively and sustain cooperation across groups. Language is a profound innovation, allowing not just the exchange of information, but the transmission of culture across generations. Without it, knowledge dies with individuals. Cooperation, too, requires a delicate balance between self-interest and group survival. On Earth, humans managed this through social structures, shared myths, and institutions, but it was hardly inevitable. Evolution could have favored other traits, strength, speed, or camouflage, leaving intelligence as a rare side branch. That civilizations emerge at all may require a narrow set of circumstances, a tight evolutionary corridor. Even when intelligence and society arise, fragility remains. Civilizations are not permanent fixtures. They depend on resources, stable climates, and social cohesion. Archaeology reveals how many cultures have risen and fallen over mere centuries or millennia. Environmental collapse, war, or disease can undo centuries of progress. For technological civilizations, fragility is even sharper. The same tools that enable exploration can be turned toward destruction. Nuclear weapons, for example, demonstrate how a single invention can threaten global survival. The fragility of civilizations suggests that even if they emerge, their lifespan may be short in cosmic terms. 1,000 years of technological society would be a blink in the history of a galaxy. If most civilizations fail quickly, the silence we hear may be the silence of fragility, a universe in which the lights go out before they spread. The concept of evolutionary filters captures this idea. At every stage, there may be barriers that prevent progress. The origin of life, the rise of complexity, the emergence of intelligence, the formation of civilizations, and the survival of those civilizations are all steps with uncertain probabilities. If any one of them is extremely rare or fragile, then the chain leading to interstellar presence is broken. From this perspective, the galaxy might be filled with half-completed experiments, microbial worlds, oceans of multicellular life without intelligence, or intelligent creatures that never form lasting societies. Each filter narrows the pathway, leaving only a tiny fraction of worlds capable of producing civilizations like ours. The absence of signals might reflect not the absence of life, but the attrition of possibilities at each stage. From this reasoning emerges the hypothesis of the Great Filter. Proposed in the 1990s, it suggests that somewhere in the sequence of steps from dead matter to interstellar civilization lies a barrier so difficult that almost no species passes it. If the Great Filter lies behind us, in the origin of life, the rise of complexity, or the emergence of intelligence, then humanity may be among the rare successes, survivors of improbable thresholds. This would make us exceptional, but perhaps lucky, living proof that the filter can be crossed. If, however, the Great Filter lies ahead in the survival of technology, the management of planetary resources, or the avoidance of self-destruction, then our silence takes on a darker meaning. It would imply that civilizations almost always fail before becoming visible across the stars. The paradox in this view is not just an abstract puzzle, but a potential warning, a shadow cast by the futures that did not last. The paradox of silence may not arise from the difficulty of beginnings, but from the hazards of advancement. One of the most immediate risks is conflict born of technology. In the mid-20th century, humanity crossed a threshold with the detonation of nuclear weapons. For the first time, a civilization gained the power to end itself through war. The stockpiles of the Cold War brought this danger to global scale, where the fate of billions could hinge on political miscalculation or malice. Nuclear fire could not only destroy cities, but collapse ecosystems, filling the atmosphere with soot and choking agriculture. This destructive potential is not unique to humanity. Any species that develops powerful weapons before it develops resilience and wisdom may face similar risks. The silence of the stars may be the silence of civilizations that stumbled at this stage, destroying themselves before their voices could reach far. Environmental collapse poses another form of self-inflicted peril. Civilizations draw resources from their planets, altering climates, consuming energy, and reshaping ecosystems. On Earth, the burning of fossil fuels, deforestation, and pollution have already destabilized the atmosphere and oceans within just a few centuries of industrial growth. Rising temperatures, acidifying seas, and collapsing biodiversity are signals of how fragile the balance can be. A technological species may discover, as we are discovering, that progress carries unintended costs. If a civilization cannot adapt or change its trajectory, the very environment that sustains it may unravel. Collapse may come not from war, but from slow attrition, a death by imbalance. The galaxy may therefore be littered with worlds where civilizations briefly flourished, only to vanish beneath their own excess. Beyond these known dangers lie those that come with advanced technologies. Artificial intelligence, if pursued without safeguards, might act in ways that undermine or replace its creators. Biotechnology carries risks of engineered pathogens that could spread beyond control. Nanotechnology, energy manipulation, and other future tools may contain hidden catastrophes. The pattern is consistent. As knowledge grows, so does power. And with power comes risk. A young civilization may find itself juggling threats that it does not fully understand. The probability of survival through these bottlenecks may be low. Each species that fails leaves no signal, no trace. In this view, the silence of the galaxy may simply be the accumulated record of failures, hidden from us by the finality of extinction. The fragility of young civilizations deepens the problem. To reach a stage where interstellar presence becomes possible requires not just invention, but endurance. Institutions must hold, cultures must stabilize, and societies must resist fragmentation. Yet human history shows how precarious these structures can be. Empires collapse, governments falter, and knowledge is lost. The longer the timeline, the more chances for disaster. A global society capable of building starships may have to survive thousands of years of instability before spreading outward. Each new century brings fresh challenges. The early centuries of technological growth may therefore be the most perilous, a crucible that only a few species survive. If the galaxy is silent, it may be because very few ever pass beyond this vulnerable stage. Of course, the dangers are not only self-inflicted. The cosmos itself is hazardous. Asteroids and comets collide with planets, sometimes with catastrophic force. Earth has experienced such events, including the impact that ended the reign of the dinosaurs 65 million years ago. Supernova, the explosive deaths of massive stars, can bathe planets in radiation, stripping atmospheres or sterilizing surfaces. Gamma-ray bursts, though rare, unleash immense energy that could scour entire regions of a galaxy. Magnetic storms, solar flares, and wandering stars all add to the list of threats. A civilization may be extinguished not by its own actions, but by the indifferent violence of the universe. In such cases, there may be no chance for recovery, no legacy left for others to find. Taken together, these dangers suggest one possible explanation for the silence: survival bias. We are here because we have, so far, survived. Every civilization that did not survive is absent from the conversation. In a universe where countless attempts may have been made, we see only the survivors, because the extinct leave no signals. The absence of evidence is not necessarily the absence of attempts, but the silence of those who failed. This perspective casts the paradox in a somber light. The galaxy may not be empty, but haunted by the memory of civilizations that never made it through their dangerous adolescence. We cannot hear them, not because they never existed, but because they are gone. And so, as we look outward, we may also be looking inward, at the fragile stage in which we now live, wondering whether we will join the silence or find a way to endure. Not every solution to the Fermi Paradox rests on rarity or destruction. Some suggest that civilizations are indeed present in the galaxy, perhaps abundant, but that they are deliberately hidden from us. This idea is known as the zoo hypothesis. It imagines that advanced societies are aware of us, but choose not to reveal themselves, much as humans might observe animals in a preserve without announcing their presence. From their perspective, Earth could be a controlled environment, a place where developing civilizations are allowed to grow without interference. Our silence, in this case, is not the result of emptiness, but of intentional restraint. We do not hear the voices of others because they have chosen to keep their distance, watching, perhaps waiting, as we mature. The unsettling possibility is that our loneliness is curated, that we are not alone but isolated by design. This idea resonates strongly with a familiar concept from human imagination, the prime directive of science fiction. In stories like Star Trek, advanced civilizations refrain from interfering with less advanced societies, believing that interference would distort natural development. If such an ethic exists in the galaxy, it could explain why we see no evidence of contact. Civilizations older and wiser than ours may abide by a principle of non-interference, declining to announce themselves until we reach a certain threshold of maturity. If the stars are full of watchers, then we are in the position of children growing within a vast and invisible community. Only when we demonstrate stability, cooperation, or technological capability might the silence be broken. Until then, we remain in a kind of cosmic quarantine, unknowing participants in a policy we did not choose. A related interpretation is that non-interference may not be motivated by principle alone, but by safety. Contact between civilizations at very different levels of development could be dangerous for both. Advanced societies may wish to avoid contaminating young ones, whether culturally, biologically, or technologically. At the same time, they may also fear risk to themselves. Even a primitive species could pose dangers if introduced too early to technologies it cannot handle responsibly. The safest course, therefore, is silence. To observe without revealing, to watch without speaking. Just as humans practice quarantine when exploring fragile ecosystems on Earth, advanced beings may practice it on a galactic scale. Our silence may be the sound of caution, a precautionary barrier designed not to harm or to be harmed. Beyond these familiar scenarios lies a more speculative thought. Perhaps our entire reality is a kind of simulation, and the absence of aliens reflects constraints of its design. If the universe is a programmed construct, then only the details necessary for our experience might be rendered. Distant civilizations may not be included because they are not needed for the purpose of the simulation. The paradox in this view is not about probability or silence, but about the architecture of reality itself. While such ideas are difficult to test, they remain part of the landscape of speculation. If the universe is simulated, then the absence of others is not surprising, for the simulation may contain only us. The silence is not a clue about the galaxy, but about the boundaries of our experience. Another perspective, darker in tone, is captured by what some call the dark forest hypothesis. It imagines the galaxy as a place filled with civilizations, but where survival depends on remaining hidden. In a forest at night, every creature is both hunter and hunted. To reveal oneself is to invite danger. In such a galaxy, civilizations would avoid broadcasting signals, would camouflage themselves, and would seek to detect others without being detected. The silence we hear then would not mean emptiness, but fear. Others may be out there listening quietly just as we are, each aware that to shout into the darkness could bring ruin. In this chilling vision, the galaxy is not quiet by accident, but by strategy. Everyone hides because no one can trust. If any of these scenarios are true, the implications for our future are profound. If the zoo hypothesis holds, then one day the silence may end abruptly when others decide we are ready. If the prime directive governs, then our growth as a civilization may determine when we join a larger community. If non-interference is driven by caution, then contact may occur only when we prove that we are safe, for ourselves and for others. If the simulation idea is correct, then perhaps no contact will ever come, for others are not part of the framework we inhabit. And if the dark forest hypothesis is true, then we must consider the possibility that silence is survival, and that our own transmissions into space carry risks we barely understand. Each possibility transforms the paradox into a different kind of mirror, reflecting not just the galaxy but our own choices. In all of them, the silence remains, but its meaning changes. Whether as guardians, programmers, or hidden neighbors, the others, if they exist, shape the silence in ways we can only guess. For more than half a century, humanity's primary search for extraterrestrial intelligence has focused on radio signals. The idea is straightforward. Radio waves can travel vast distances through space, passing largely unimpeded by gas and dust. A sufficiently strong transmission could, in principle, be detected across interstellar ranges. Radio telescopes have scanned the skies, listening for narrowband tones or repeating patterns that might indicate an artificial source. Yet after decades of searching, no confirmed signal has been found. This raises the possibility that our strategy may be limited. Perhaps other civilizations do not use radio in ways we expect, or perhaps their transmissions are too weak, too brief, or too different from what we are tuned to here. The silence may not mean they are absent, but that we are listening incorrectly, or to the wrong channels altogether. Much of Radio SETI has focused on narrowband signals, those confined to extremely small slices of frequency space. Such signals are easy to distinguish from natural sources, which usually spread across broad bands. A single sharp tone stands out, like a whistle in a noisy crowd. But civilizations may not favor narrowband communication. They may use broadband signals, spread across wide frequencies, appearing as noise to us. They may employ methods we do not recognize, such as frequency hopping or encrypted modulation. What seems like random static might in fact be sophisticated communication beyond our decoding. If our assumptions about signal structure are too narrow, we may overlook messages flowing past us continuously. Our search may be missing not because no one is speaking, but because we do not yet understand their language. Beyond this, there is the possibility that advanced civilizations have moved beyond radio altogether. Just as humanity has transitioned from telegraphs to fiber optics, from bulky transmitters to satellites, so too might others have advanced to technologies unfamiliar to us. They could communicate through tightly collimated laser beams, directed from star to star. They could employ neutrinos, gravitational waves, or quantum entanglement, exotic channels that leave little trace for our instruments. The universe might be alive with communication invisible to us, taking place in media we cannot yet harness. To interpret silence as absence may therefore be premature. It may be only the silence of our limited perspective, a technological blind spot in which we wait, ears pressed to the wrong walls. Another reason for quiet may be efficiency. As civilizations mature, they may minimize energy leakage. Early radio technology on Earth produced strong emissions, spreading outward in all directions. But modern systems are increasingly focused and efficient, reducing unintended broadcasts. If other societies followed a similar path, their presence would become harder to detect over time. The galaxy may have passed through a noisy adolescence long ago, leaving only whispers. Civilizations that endure may be quiet by necessity, conserving energy, optimizing communications, or preferring privacy. We may therefore expect not a chatter of signals, but a profound hush. The paradox is sharpened by this recognition. Silence may not imply failure or destruction, but success. The most advanced societies may be the most invisible, their technologies woven seamlessly into their worlds. If civilizations cannot be heard through signals, perhaps they can be seen through their works. The concept of astroengineering imagines societies altering stars, planets, or entire systems to suit their needs. Vast solar collectors, orbiting mirrors, or artificial structures could leave detectable signatures. A star partially obscured by orbiting platforms might dim in peculiar ways. Waste heat from enormous machines might glow in infrared. Such signs would not require intentional communication, only the byproducts of existence. The search for astroengineering is still in its infancy, but it offers a different approach to the paradox, to look not for voices, but for footprints. If the galaxy has builders, their works may shine even if they remain silent. Among the most famous ideas of this kind is the Dyson sphere, proposed in the 1960s. Physicist Freeman Dyson suggested that a sufficiently advanced civilization might surround its star with a swarm of collectors, capturing much of its energy output. Such a structure need not be a solid shell, but could consist of countless satellites orbiting in complex patterns. To outside observers, the star would appear dimmer in visible light, but brighter in infrared, as waste heat leaked away. Surveys have searched for such anomalies, scanning millions of stars for unusual energy distributions. A few candidates have been noted, such as the mysterious dimming of Tabby's star, though natural explanations remain most likely. The idea of Dyson spheres illustrates how we might detect civilizations not through what they say, but through what they build. Megastructures, stellar modifications, or galaxy-scale projects could stand as beacons of presence, even in the absence of deliberate contact. Whether we find such signs remains uncertain, but the search broadens the horizon of possibility. Silence in one channel may not mean silence in all. One response to the paradox is that while life may not be impossible, the conditions that allow complex technological civilizations may be extraordinarily rare. This perspective is sometimes called the rare Earth hypothesis. It argues that Earth is not an average planet but an exceptional one. the product of a chain of favorable accidents. Our location in the galaxy, our distance from the Sun, our magnetic field, plate tectonics, and even the presence of our unusually large moon may all be factors that align in unlikely ways. Each element may be uncommon on its own, but together they create a system balanced for long-term stability. If most planets lack these features, then Earth may be one of very few that sustain complex life. In that case, the silence of the galaxy is not a puzzle, but an expectation. The void is quiet because few other worlds have the intricate conditions we take for granted. Even when conditions are favorable, catastrophes loom. Planets can suffer events that reset or extinguish biology. Massive impacts can boil oceans or shroud atmospheres in dust for centuries. Volcanic supereruptions can poison skies and collapse ecosystems. Shifts in a planet's orbit or axial tilt can drive climates into extremes, freezing or burning away the possibility of stability. On Earth, mass extinctions have occurred repeatedly, wiping out vast fractions of life. Each time, recovery has taken millions of years. A civilization may never arise if its world is struck too often or too severely. Catastrophe acts as a gatekeeper, keeping most planets locked in cycles of boom and collapse, never progressing to enduring complexity. The galaxy may therefore be filled with promising beginnings undone by disaster before they can flower. The broader environment of a galaxy also plays a role. Not all regions are equally hospitable. Astronomers speak of galactic habitability zones, areas where conditions are stable enough to permit life. Too close to the galactic center, stars are packed tightly, radiation levels are high, and gravitational disturbances are frequent. Too far in the outskirts, there may be insufficient heavy elements to form rocky planets. The zone of balance lies somewhere in between, where stars are abundant but not overcrowded, and where planetary formation can produce a variety of worlds. Earth, as it happens, sits within this temperate band. But most of the stars in the Milky Way lie outside it, in harsher neighborhoods. If habitability depends on galactic address, then life-bearing worlds may be the exception, not the rule. Even within habitable zones, subtle features shape outcomes. Jupiter, the giant planet of our solar system, plays a protective role by deflecting or absorbing comets and asteroids. Without such a guardian, Earth might suffer impacts too frequently for complex life to endure. Likewise, our moon stabilizes Earth's axial tilt, preventing wild swings that could destabilize climate. Plate tectonics recycle carbon, maintaining long-term balance between greenhouse gases and temperature. Each of these features may be uncommon elsewhere. Many planetary systems may lack giant planets in the right orbits, or moons of the right size, or geological activity sustained over billions of years. A planet might be habitable in theory, but unstable in practice. Civilizations require not just the spark of life, but the shelter of stability, and stability may be rare. The frequency of sterilizing events further narrows the field. Supernova, gamma-ray bursts, and other high-energy phenomena can scour entire regions of a galaxy. A planet near one of these events may see its atmosphere stripped or its surface sterilized in moments. Even without total annihilation, repeated radiation pulses could suppress the development of complexity, resetting biospheres before civilizations have a chance to rise. Our own position in the galaxy appears relatively calm, shielded from such frequent calamities. But this may not be true elsewhere. Across the billions of stars, countless worlds may be struck again and again, trapped in cycles of destruction. From this perspective, habitability is not only rare, but fragile, easily lost in the storms of cosmic violence. All of these factors combine to paint a picture of patchy habitability. The galaxy is not uniformly welcoming. It is a landscape of scattered oases in a desert of inhospitable worlds. Some planets may have water but no stability. Others may endure catastrophes too often to progress. Many may orbit stars that flare unpredictably, stripping atmospheres or frying surfaces. A few, like Earth, may thread the needle, balancing on the narrow ridge of stability long enough for civilizations to emerge. In such a patchwork, silence is natural. The galaxy may be full of worlds, but few of them offer the delicate blend required for sustained complexity. The paradox, in this view, is softened. We do not hear others because they are rare, not because they never were. We are scattered islands in a vast sea, distant and quiet, each separated by expanses too great to bridge. The silence of the galaxy may hold a sobering implication. Perhaps we are rare. Humanity may not simply be one among many, but one among very few, possibly the only civilization to arise in this corner of the cosmos. To imagine ourselves as rare is to see our species not as a trivial footnote, but as an unlikely spark. The billions of stars surrounding us may host countless worlds where chemistry stirred, but never crossed into complexity, or where evolution stalled before intelligence took root. If that is true, then our existence becomes an extraordinary exception. Rarity does not inflate our importance, but it does reshape our perspective. We may not be ordinary participants in a galactic conversation, but lone speakers, our words carrying into a silence unbroken by reply. To live with this possibility is to recognize both our fragility and our uniqueness. If we are rare, then with rarity comes responsibility. To be among the first, or perhaps the only, places upon us the task of stewardship. We hold in our hands not just our own future, but perhaps the future of life and intelligence in this region of space. If no one else has crossed the hurdles, then we may be the trailblazers. Our survival, our choices, and our ability to extend beyond Earth could determine whether intelligence continues in the galaxy at all. This does not mean we are destined for greatness, but it does mean that our failures would echo into emptiness. The silence of the stars may not be a comfort, but it can serve as a reminder that our actions carry weight beyond our planet. We are, perhaps, the fragile carriers of a light that otherwise may never shine again. For our own future, the silence can be interpreted in different ways. It may be a warning, suggesting that the obstacles ahead are formidable, that civilizations rarely endure long enough to spread. Or it may be an opportunity, showing us that the field is open, waiting for us to fill it. Either way, the absence of others frames our path. If no one else is coming, then the responsibility for expansion, exploration, and endurance falls upon us. Silence, in this sense, is not only an absence, but a challenge. What we make of it will define the trajectory of our species, whether we remain confined to one world or extend into the wider cosmos. In the present day, our attempts to listen and to search continue. SETI projects use increasingly sensitive instruments, scanning more stars, more frequencies, and more patterns than ever before. New radio arrays, optical searches for laser flashes, and surveys of planetary systems expand the possibilities. Future telescopes, such as the Square Kilometre Array, promise orders of magnitude improvement in sensitivity. Beyond listening, we are also exploring exoplanets, characterizing their atmospheres in search of chemical signs of life. Methane, oxygen, or unusual chemical mixtures might reveal biology even in the absence of technology. SETI today is not confined to one method, but is diversifying, looking for signals, footprints, and biosignatures across the sky. The search itself is part of how we live with the silence, by refusing to stop asking the question. At the same time, we are taking first steps into our own solar system. Robotic missions to Mars, Europa, and Titan seek to uncover whether life exists beyond Earth. Colonies on the Moon or Mars, still in the distant future, would mark the beginning of humanity as a multi-planet species. Each expansion outward reduces the fragility of our existence, distributing life beyond a single world. If we continue, we may someday send probes to nearby stars, or construct vast habitats in space. To expand is not only to explore, but to safeguard, ensuring that life endures even if catastrophe strikes our home. The silence of the stars does not forbid such progress. It may even invite it, urging us to carry life outward where others have not. Ultimately, the paradox may be less a problem to solve than an invitation to wonder. To live in a galaxy where silence reigns is to live with mystery. Each star we see is a possibility, each planet a question mark. The absence of contact does not diminish the grandeur of the cosmos, but amplifies it. The paradox draws us into reflection on probability, on fragility, on the unknown. It encourages humility, reminding us that we may be unique, and curiosity, reminding us that we may yet find company. Whether the silence is permanent or temporary, whether it reflects rarity, fragility, or concealment, it holds us in a state of questioning. And perhaps that questioning is itself valuable. In seeking others, we learn more about ourselves. In searching the sky, we recognize the strangeness of our own existence. The paradox does not close the door on possibility, it opens it wider, inviting us to dream of futures in which the silence may one day be broken. If advanced civilizations exist, their messages may not come to us in the form of radio waves at all. Instead, they might write across the sky itself, leaving imprints in the stars that endure for millennia. This idea, stellar engineering as communication, suggests that the cosmos itself could serve as a canvas, a medium where beacons and symbols might be built into natural processes. Civilizations capable of harnessing energies on stellar scales would have the means to alter the very light of stars. A change in a star's brightness, its rhythm, or its chemistry could serve as a message more enduring than any broadcast. While the radio signal might fade, a stellar modification could last for millions of years, patiently waiting to be observed by anyone able to notice. The notion is not entirely speculative. In the 1960s, when pulsars were first discovered, astronomers briefly considered the possibility that they were artificial. These objects, neutron stars rotating rapidly and emitting beams of radio waves, produce signals with astonishing regularity. Some pulsed dozens or hundreds of times each second, with timing so precise that they rival atomic clocks. At first, the sheer steadiness and narrowness of their beams suggested something unnatural, leading scientists to nickname the first discovered source LGM1 for Little Green Men. It was soon understood that pulsars were natural phenomena, the remnants of supernova explosions, but the moment of uncertainty revealed how easily a cosmic beacon might masquerade as a star. If a civilization wished to create a recognizable signal, they might exploit similar astrophysical mechanisms, sculpting patterns into objects we already watch. Could stars themselves be used as beacons? In principle, yes. A civilization capable of manipulating stellar output could modulate its brightness in ways that would appear anomalous. A steady star could be made to flicker with deliberate regularity, or its spectral lines could be adjusted to spell out patterns. Large-scale structures orbiting a star could dim its light in coded intervals, much as we send data through pulses of electricity or flashes of light. Such messages would not need to be aimed or repeated constantly. Once established, they could endure, visible to any observer who notices the pattern. The star becomes the transmitter, its light carrying the message across the galaxy with no further energy cost. Astronomers already study stellar light curves, tracking how stars brighten and dim over time. Exoplanet discoveries, for example, often come from noticing the tiny dip in brightness as a planet passes in front of its star. But such light curves could also contain signatures of artificiality. If an orbiting array of satellites or mirrors were arranged in deliberate geometries, the resulting pattern of dimming would differ from a natural planet. Repeated signals, prime number sequences, or other mathematical regularities might stand out as unmistakably artificial. In principle, a civilization could use its own star as a lighthouse, broadcasting identity and intent through geometry written in light. The question is whether we would recognize such a signal for what it is. The prospects of decoding messages hidden in starlight are tantalizing but uncertain. Astronomy deals with vast datasets, much of which appear noisy or irregular. Distinguishing natural variability from deliberate modulation is difficult, especially when our catalogue of natural phenomena is incomplete. Many stars vary in brightness naturally through pulsations, spots, or eruptions. An artificial signal might be overlooked as another instance of astrophysical complexity. Alternatively, we might already have seen anomalies but not recognized their significance. Tabby's star, famous for its unusual dimming patterns, sparked speculation about possible megastructures, though natural explanations remain more likely. Still, the case demonstrates how closely the search for exoplanets and the search for intelligence overlap. In both, we are reading the fine print of stellar light. Why might such communication remain invisible to us? One reason is scale. Even if civilizations use stars as beacons, the number of stars is vast, and our ability to monitor them continuously is limited. Signals might be rare, subtle, or visible only in certain wavelengths. Another reason is expectation. We may not know what patterns to look for. Our algorithms designed to find exoplanets or catalog variability may not be tuned to detect intelligence. It is also possible that the chosen form of communication is too advanced for us, encoded in ways that require knowledge we do not yet have. The silence may not reflect absence, but a mismatch between signal and receiver. Messages may already be written in the stars, but our eyes and minds are not yet trained to read them. When we imagine life beyond Earth, we often project our own biology outward. We picture forests of green plants, oceans filled with fish-like creatures, or societies of beings with familiar limbs and faces. This tendency is sometimes called carbon chauvinism, the assumption that life must be carbon-based and Earth-like. Carbon does have remarkable properties. It forms long, stable chains, creates a vast diversity of molecules, and supports the complexity of proteins and nucleic acids. On Earth, it is the foundation of every living system. But the universe is vast, and to assume that life must mirror us may be to limit our imagination. The silence of the galaxy could reflect not absence, but our narrow expectations. Life may exist, but in forms so unfamiliar that we do not yet recognize it. One of the most often suggested alternatives is silicon-based life. Silicon sits just beneath carbon on the periodic table and shares some of its bonding properties. It can form long chains and complex structures, though it is less flexible than carbon. In certain environments, particularly at high temperatures where silicon compounds are more stable, silicon chemistry might provide the backbone for biology. Imagining such life leads to visions of organisms with rock-like tissues, or metabolisms that rely on silicate reactions rather than organic ones. While no examples exist on Earth, the abundance of silicon in the universe keeps the possibility alive. If civilizations arose from such chemistries, their biology and technology might appear utterly alien, invisible to methods designed to detect carbon signatures. Another expansion of possibility comes from solvents. On Earth, water is the universal medium of life, dissolving salts, transporting molecules, and enabling chemical reactions. But other liquids might serve similar roles. Ammonia, with its polarity and hydrogen bonding, could act as a solvent under colder conditions. Methane and other hydrocarbons, though less versatile, might provide environments for slower but still functional biochemistry. Saturn's moon Titan, with its methane lakes and thick atmosphere, stands as a natural laboratory for such speculation. If life evolved there, it would not resemble Earth's biology. Its cells might be built from completely different membranes, its metabolism driven by chemical cycles alien to us. To search only for water-based life may be to overlook worlds alive in their own way, whispering with chemistries we do not yet understand. Beyond chemistry, some had speculated about forms of life not based on matter as we know it. Could plasma in stars organize into self-sustaining patterns? Could magnetic fields form coherent structures that behave like organisms? These ideas remain speculative, but they push the boundaries of what life might mean. If intelligence can arise from stable, self-replicating patterns, then the medium may be less important than the dynamics. In this view, stars themselves could harbor consciousness, not in the form of brains or bodies, but as emergent patterns within plasma and magnetism. If so, the galaxy might be alive in ways we have not yet conceived, and the silence we experience may be because we do not know how to converse with entities so different from us. The challenge, of course, lies in defining life. On Earth, life is recognized by metabolism, reproduction, and evolution. But these criteria are rooted in carbon-water biology. If organisms operate on principles outside this framework, they may fail our tests. We may look for oxygen in atmospheres, for chlorophyll-like pigments, or for carbon-based molecules, and miss entirely the signatures of other systems. Even our telescopes and instruments are biased, designed to seek Earth-like traits. The silence may therefore be self-imposed, the product of our narrow filters. To broaden our search, we must broaden our definition of the living, opening ourselves to chemistries and dynamics that challenge our preconceptions. This raises a sobering possibility. Perhaps we are surrounded by life we cannot recognize. Entire worlds might teem with activity invisible to our senses. Cultures might thrive with metabolisms beyond our comprehension, and stars might host intelligences that we dismiss as physics. The paradox, then, is not that we are alone, but that we are blind. Our assumptions, built from the singular case of Earth, may hide from us the richness of the cosmos. To move beyond carbon chauvinism is to accept that life may come in forms that unsettle us, that the others we seek may be unrecognizable neighbors, dwelling in chemistries and states of matter we have yet to embrace. When we imagine other civilizations, we often picture them rooted to planets, much as we are, building cities on their home worlds and sending signals across space. But this assumption may limit us. Perhaps the most advanced societies are not planetary at all, but nomadic, living in the void between stars. Freed from the risks of planetary catastrophes, asteroid impacts, climate instability, volcanic upheavals, a civilization could thrive aboard vast habitats drifting in interstellar space. Their resources might be drawn from asteroids, comets, or captured energy. Such societies would be harder to detect because they would not alter planetary atmospheres or leave signals tied to a star. The silence we hear may therefore be the silence of wanderers who have chosen not to remain bound to worlds like ours. The concept of generation ships provides one vision of such movement. If interstellar travel is too slow for a single lifetime, then entire communities could live aboard enormous vessels, crossing the distances over centuries or millennia. Within such ships, children would be born and die without ever seeing a planetary surface, their culture adapted to life in enclosed habitats. Migration between stars might not be a grand expansion, but a slow diffusion, ships moving gradually outward in patterns invisible to our brief observations. A civilization spread in this way would leave little trace visible from afar. Their light would be faint, their emissions minimal, their progress too slow to notice within our narrow window of observation. If over millions of years such migration could fill the galaxy quietly, without the obvious signs we expect, rogue planets, worlds ejected from their systems, drifting freely through interstellar space, offer another avenue for nomadic life. These planets may be far more common than we once thought, perhaps outnumbering the stars themselves. Though cold on their surfaces, they could harbor subsurface oceans warmed by internal heat. If life arises there, it could persist in hidden seas, insulated from the emptiness outside. For civilizations, rogue planets might serve as vessels, carrying communities across the galaxy without need for ships. To live on such a world would be to dwell in eternal night, lit only by geothermal warmth, but it could provide stability over immense timescales. If intelligence thrived there, we might never detect it, for such planets are nearly invisible against the darkness of space. In addition to natural wanderers, civilizations might create their own emissaries in the form of interstellar probes. Rather than sending fragile biological beings across light years, they could dispatch machines, self-replicating explorers that harvest materials and build copies of themselves. These artificial children could spread much faster than living colonists, fanning out across the stars. Such probes might be tiny, hidden in the vastness, or disguised as natural objects. Some thinkers have even suggested that probes might already be in our solar system, undetected among asteroids or comets. If civilizations rely more on probes than on radio broadcasts, then our failure to hear them may reflect our failure to look in the right way. The galaxy could be threaded with the quiet presence of machines, unnoticed because we are not searching for their subtle signatures. Directed panspermia is another possibility, the deliberate seeding of life across planets. Rather than waiting for natural evolution, civilizations might spread biology, sending spores or engineered organisms to seed new worlds. Over billions of years, this could populate the galaxy with life, even if civilizations themselves did not last. Some have speculated that life on Earth may even have arrived in this way, though no evidence yet supports it. If directed panspermia is practiced, then the galaxy may be alive not because life arises easily, but because it is planted deliberately. In such a scenario, civilizations may act less as broadcasters and more as gardeners, leaving no signals, only the quiet growth of biology where once there was none. Mobility changes detectability. Civilizations on planets alter atmospheres, use energy in ways that produce emissions, and build structures that can be observed. Nomadic civilizations, by contrast, might leave no such traces. They might choose stealth to avoid attention or efficiency that produces little waste. They might disperse slowly, blending into the background. Their presence would not be obvious in radio surveys or planetary scans. The paradox may therefore not reflect absence, but difference. Others may be here, but moving in ways that leave no mark we can yet see. To live with the silence is to consider that what we expect, bright signals, bustling planets, may not match reality. The others, if they exist, may be moving through the galaxy like shadows, carrying life quietly from star to star, unseen, but present in the great night. So far, much of the paradox has been considered from the scale of our galaxy. Yet the universe is larger still. Beyond the Milky Way lie trillions of other galaxies, each with billions of stars. If life is possible here, it should be possible there, From an intergalactic perspective, the silence grows even more puzzling. With so many galaxies, the number of possible civilizations should be immense. And yet, no signals, no travelers, and no signs of intervention appear across the great voids that separate us. Perhaps the paradox is not simply galactic, but universal, a quietness that extends across cosmic scales. One reason may be that the Milky Way is isolated in practice. While neighboring galaxies like Andromeda are relatively close in astronomical terms, a few million light-years away, the distances are still enormous. The energy required to cross between galaxies is far greater than that required to cross the Milky Way itself. Even a civilization capable of spreading across its home galaxy might find intergalactic travel prohibitive. They could exist in abundance elsewhere, but remain forever confined to their own islands of stars. In such a universe, we should not expect to hear from them, because the void between galaxies acts as a natural barrier, a moat so vast that even the most advanced species may not cross it. The barriers are not only of distance, but of physics. The voids between galaxies are thinly populated with gas and dark matter, offering little in the way of resources for travelers. A starship making the journey would face immense challenges in energy, navigation, and survival. Even if probes or generation ships attempted the crossing, the timescales might be tens or hundreds of millions of years. Such efforts could occur, but they would be so rare and so slow that the odds of encountering one are negligible. The vast emptiness between galaxies may therefore ensure that civilizations remain permanently local, visible to themselves, but invisible to each other. Could others exist beyond our detection horizon? The observable universe is bounded not by physical walls, but by the speed of light and the age of cosmic expansion. We can only see as far as light has had time to reach us since the Big Bang, some 13.8 billion years ago. Beyond that lies a universe we cannot observe. If civilizations thrive there, their light has not yet arrived and may never arrive. Even within the observable universe, the faint signals of distant civilizations may be drowned out by distance and time. Light weakens, signals fade, and galaxies recede. The silence may therefore not indicate absence, but limitation. Our instruments, confined to one small vantage, cannot probe far enough to hear the chorus, if chorus there is. Cosmic expansion sharpens this problem. The universe is not static, but growing. Space itself stretching between galaxies. Distant galaxies recede from us faster than light, carried away by expansion. Any civilizations they contain are already lost to us, forever beyond communication. The window of possibility shrinks over time. Each epoch closes off more of the universe, as expansion carries it beyond reach. If contact has not yet been made, it may never be made, because the fabric of space-time itself is erasing opportunities. The silence we hear may therefore be permanent, not because others do not exist, but because the universe is pulling them away faster than we can follow. In this light, silence becomes a property of separation. Vast gulfs of space, bounded by the speed of light and stretched by expansion, ensure that civilizations are islands, unable to reach one another. Each galaxy becomes its own bubble of possibility, filled or empty, but isolated from its neighbors. The paradox, then, is not why we do not hear voices from afar, but why we expect to. The void itself guarantees isolation. To live in the Milky Way is to live in one small pocket of a much larger reality, connected only to what lies within our galactic walls. Beyond them, silence is not puzzling, but inevitable, a structural feature of the cosmos itself. The silence of the cosmos is not only a scientific puzzle, it is also a profound psychological weight. When we turn our eyes to the night sky and find no answer, the quiet stirs emotions older than science itself. Humans are social creatures, accustomed to voices and presence. To extend that expectation outward, to assume that the stars too must hold companions, is natural. When those companions fail to appear, we feel isolation not merely as a fact, but as a burden. The paradox is therefore as much about our minds as about the universe. Throughout history, myths and religions have filled this silence. Gods, spirits, and celestial beings provided a sense of company, an assurance that we were not alone in the great expanse. The heavens were populated with intelligences, some benevolent, some indifferent, some hostile. Astronomy stripped away these presences, replacing myth with emptiness. Yet the yearning remains. To imagine extraterrestrials is in part to restore that ancient sense of a peopled cosmos. The Fermi Paradox, therefore, touches something archetypal, the tension between the need for companionship and the reality of silence. The possibility that we are alone brings with it existential risks. If humanity is the sole intelligent species, then the responsibility we bear is immense. We become the only voice capable of contemplating the cosmos, the only consciousness able to give meaning to its vastness. This thought can be ennobling, but it can also be crushing. The fragility of our species stands in stark relief. A single catastrophe, war, disease, or environmental collapse could silence not just Earth, but the universe's only reflective voice. The paradox therefore forces us to confront vulnerability at a cosmic scale. Coping with emptiness has become a theme of philosophy as well as science. Some embrace it as a call to self-reliance. If the universe is silent, then we must fill it with our own meaning. Others see it as an invitation to humility. If the stars hold no answer, then our smallness must be accepted, not resisted. Still others find comfort in uncertainty itself, in the possibility that silence is temporary, that voices may yet emerge with time. In this way, the paradox becomes a mirror of our own inner states, reflecting fear, hope, and wonder back at us. Culture has been shaped by this silence as well. Works of art, literature, and film often portray alien contact as a moment of revelation, the breaking of a cosmic loneliness. The lack of such contact keeps the longing alive, fueling stories that try to imagine what silence with company might feel like. Even in speculative science fiction, the paradox lurks. Why is first contact always in the future, never in the present? The silence is a narrative force, shaping our imagination as much as our science. Ultimately, the paradox is a psychological mirror. It reveals not only what the universe may or may not contain, but also what we expect and desire. Our interpretations of silence reveal our values, whether we long for companionship, fear for survival, or embrace solitude. The quiet cosmos presses us to ask who we are and why we seek others at all. Perhaps the most enduring impact of the paradox is not in astronomy, but in the human heart, where the unanswered question becomes a lens through which we see ourselves more clearly. If silence defines the present, the future remains open. The Fermi Paradox does not end with what we have not heard, but with what we may one day hear. To imagine possible futures of contact is to explore both hope and caution, both optimism and restraint. For the first time in history, humanity possesses tools capable of probing the stars not just with wonder, but with intent. The next century may hold answers that eluded all of human history before us. Possible scenarios vary widely. One is a slow, gradual discovery, the detection of a faint, unambiguous signal buried within radio noise, a pattern too regular to be natural. Such a signal might originate from a civilization long gone, a relic rather than a greeting, its transmission echoing across millennia. Another possibility is sudden and dramatic, the unmistakable engineering of a star's light, or the detection of a vast structure dimming its host. Still another is indirect, the discovery of a world with clear biosignatures and eventually technosignatures revealed through spectra. Each scenario reshapes humanity in a different way, but all alter our sense of aloneness. If contact were ever to occur, the next step would be diplomacy, though not in the traditional sense. Vast distances make two-way communication slow. A message sent to a nearby star could take decades to arrive, and decades more for a reply. Instead of conversation, the reality may be more like correspondence stretched over centuries. To prepare for this, humanity may one day establish permanent listening posts, not just to receive, but to carefully craft what we send. Interstellar diplomacy may be less about negotiation and more about curating our story for an audience that may or may not exist. Alongside hope lies risk. Broadcasting our presence might invite dangers we cannot foresee. The possibility that the universe is a dark forest, where survival depends on silence, has led some to argue for caution. Others counter that our planet already leaks signals, from radio and radar to city lights visible from afar. The debate reflects deeper fears, that to reveal ourselves is to risk vulnerability, and that the silence of the cosmos may be the silence of self-preservation. Every choice about what to send carries weight, shaping not only how others might see us, but whether others ever hear us at all. True contact, if it ever happens, may require more than technology. It may demand maturity. Civilizations capable of enduring long enough to reach the stars must overcome their own fragilities. War, ecological collapse, or uncontrolled technology could end them before they begin. To last for tens of thousands of years, a society must learn not just how to build machines, but how to survive themselves. Contact, then, might only occur between species that have mastered longevity, patience, and restraint. If so, the silence we hear now may simply mean we are still too young to be admitted to the conversation. The time horizon of discovery is therefore long. It may not be years or decades, but centuries or millennia before definitive contact occurs. Our telescopes improve, our instruments sharpen, and yet the cosmos may keep its secrets for ages still. The paradox stretches across time as well as space, reminding us that human history is a thin slice of cosmic history. What feels like an eternity of waiting to us may be the briefest flicker of anticipation in universal terms. And so, how might the paradox end? Perhaps it will end with a signal, unmistakable and clear. Perhaps it will end with evidence of structures beyond imagining. Or perhaps it will never end, and silence will remain the permanent condition of the universe. In that case, the paradox itself becomes the answer, a reminder that expectation and reality do not always align, and that the universe may be more solitary than we dared to believe. Whether resolved or not, the paradox will continue to guide our questions, shaping how we listen, how we dream, and how we imagine futures of contact yet to come. As the night deepens and the stars keep their silent watch, we find ourselves once more in the quiet of the cosmos. We have wandered across scales of unimaginable size, through questions of life and death, through possibilities both hopeful and unsettling. And yet, after every path explored, the silence remains. The sky above offers no reply. It waits, calm and indifferent, a canvas painted with unanswered wonder. The mystery continues. The Fermi Paradox does not close with a solution, but with an opening, a doorway into possibility. Perhaps the silence means we are rare, perhaps it means others are cautious, or perhaps it is simply the way of things. in the universe governed by distance and time. Whatever the cause, the question endures. It shapes science, culture, and imagination, pulling us forward into futures we cannot yet see. In the stillness, our curiosity finds both frustration and fuel. And so, we drift back from the stars, carrying with us both silence and wonder. These questions will outlast us, perhaps echoing through generations, each listening for a reply that may or may not come. For now, though, the cosmos is quiet, and it is enough simply to rest beneath its vastness. May your thoughts soften, your breathing slow, and your mind find peace as you let go of the night's reflections. And so, under the quiet stars, the story continues. I hope you sleep well and dream softly. Good night.